Hi everyone, welcome to GoClasses. In the last lecture, we were discussing expanding opcode technique. I told you to solve all the gate PYQs on the expanding opcode technique. Yes or no? In the previous lecture, I gave you each and every gate PYQ on this topic. Now let's discuss all the gate questions based on expanding opcode technique. Okay, so let's start. This concept we have already seen. We have seen the complete analysis of expand opcode technique. We have seen the concept. I can say we have seen two methods. What are those? If some instruction set is given to you and the question is asking, is this instruction set possible or not? Okay, using expand opcode technique, some instruction set is possible or not, then you can apply the bit pattern method. What you can do, you can solve that question using bit pattern method. Okay, and if that instruction set is possible, then what you can do, if that instruction set, given instruction set, if that is possible using expand opcode technique, if that is possible, then you can do the encoding also. Yes or no? You can do the encoding. So that also we have seen. We have also seen the decoding logic, how the decoding will happen. That decoding logic also we have seen. So basically everything that you need to study, the complete analysis, the complete concept of expand opcode technique, we have already seen in the previous lecture. Now let's start the gate previous year questions. Let's start with this question. This is GATE 1988 question on expand opcode technique. Using an expand opcode encoding for instructions, is it possible to encode all the following in an instruction format shown in the below figure? Justify your answer. Okay, so this is given to you. Let's solve this question. This is quite simple question. Let's solve it. So remember this question, what this question is asking, that using expand opcode encoding for instructions, you have to use the expand opcode technique. Now the question is asking, is it possible? This is what question is asking. The question is asking, is it possible to encode? Okay, is it possible to encode? This is what the question is asking. Is it possible to encode all these instructions? Okay, so all of the following in an instruction format. Okay, so very simple point. Tell me which method you will use, which method you are going to use to solve this question. Remember the question is asking, basically, is this instruction set possible? This instruction set is given to you. What you want? 14 double address instructions you want, 127 single address instructions you want 60 zero address instructions you want. Okay, so this is the instruction set is given to you. Okay, what is this? This is the instruction set. Now the question is asking, is this instruction set possible or not? Is this instruction set possible or not? This is what the question is asking. So you can solve this question using the bit pattern method. That is the quickest method. Okay, so what is the bit pattern method? This question you can solve using method number 1. What is the method number 1? The method number 1 is bit pattern method. Okay, bit pattern method. So this is a very quick method. This is the quickest method, I can say. This is the quickest way. Okay, so let's solve this question using the bit pattern method. You can see what is the size of instruction. Tell me what is the size of instruction. You can see here the size of instruction. Here you can see. Tell me what is the instruction size. What is the instruction size? The size of instruction. So the size of instruction, that is 4 plus 6 plus 6. Okay, 4 plus 6 plus 6, that is your 16 bits, right? Okay, so instruction size that is already given to you, that is your 16 bits. Okay, so remember in this method number 1, you can see that instruction size you already have. What is the instruction size? That is 16 bits. Okay, these are fixed length instructions, right? Yes or no? These are fixed length instructions, means every instruction has the same length. Every instruction is 16 bits long. So you can see these are fixed length instructions. Okay, now you tell me one thing. If you have 16 bits, then using 16 bits, how many bit patterns you can create? If you have 16 bits, then how many bit patterns are possible? Because remember, instruction size is already given to you, that is 16 bits. These are fixed length instructions. You know what is the instruction? Every instruction is binary, that you already know. Every instruction, what is that? That is a sequence of 0, 1. Inside your computer, everything is binary. So remember, instruction is also binary. Now you have a 16-bit instruction. So tell me how many bit patterns are possible? What is the total number of bit patterns possible? The question, my question is, what is the total number of bit patterns possible? Okay, what is the total number of bit patterns? How many 0-1 sequences are possible? How many bit sequences are possible? Okay, or I can say how many encodings are possible? Okay, how many encodings are possible? So tell me, how many bit patterns possible? Possible. So that will be 2 power 16. Yes or no? These many bit patterns will be possible because you have 16 bits instruction size. Every instruction is binary. Every instruction is a sequence of 0, 1. Inside your computer, everything is binary. So you can see instruction is also binary. Now, your instruction has fixed length, that is 16 bits. Using 16 bits, how many bit patterns you can create? How many encodings you can create? How many bit patterns are possible? So that is 2 power 16. These many bit patterns are possible. These many bit sequences are possible. Okay. Now you can notice that some of these patterns, so you can see 2 power 16, these many bit patterns are possible, right? Okay, these many bit patterns possible. Now you can see some of these patterns will be used by 3 address instructions, some of them will be used by 2 address instructions, and some of them will be used by 1 address instruction. Yes or no? You can see 2 address, 1 address, 0 address. So very simple point that these are the bit patterns that are possible. Now here I can say what I can say. I can say that some of these bit patterns, some of them will be used by whom? Some of them will be used by 2 address instructions. So some of them will be used by 2 address instructions. Okay, some of them will be used by 1 address instructions. Some of them will be used by 0 address instructions. Okay, is this clear? Very simple. So very simple point, because remember your 2 address instruction that also has 16 bits. So you can see these many bit patterns are possible. 2 power 16 bit patterns are possible. So from these bit patterns, you can see some of them will be 2 address instruction, some of them will be 1 address instruction, some of them will be 0 address instruction. Okay. Now you tell me how many encodings are used by 0 address instructions, how many bit patterns are used by 1 address instruction, and how many bit patterns are used by 2 address instruction. Okay, so you can easily see that how many bit patterns are used by. Remember what is this? Here I will put the value, that is the number of bit patterns. Okay, here what I will do, I will put the value, that is number of bit patterns used by, or I can say consumed by, or I can say used by 2 address instruction, 2 address instructions. Okay, plus how many bit patterns are consumed by 1 address instructions, plus how many are consumed by 0 address instructions. Yes or no? So the same thing, basically number of bit patterns used by 1 address instructions. Okay, 1 address instructions, and plus how many number of bit patterns used by 0 address instructions. Now you tell me one thing, just tell me one thing, how many bit patterns are used by 2 address instructions, plus how many of them are used by 1 address instructions, plus how many are used by 0 address instructions. So you tell me this total, this will be less than equal to what? This will be less than equal to 2 power 16, because these are the total number of bit patterns possible. You can see total number of bit patterns, how many are there? Your instruction size is 16 bits. So you can see how many bit patterns are possible. 2 power 16 bit patterns are possible. Yes or no? These many bit patterns are possible. Now you already know that every instruction, if you have 2 address instruction, that also will be one of these patterns. Yes or no? Every 2 address instruction, that is one of these patterns. So you can see these many bit patterns we have. From these bit patterns, from these 2 power 16 bit patterns, some instructions are 2 address instructions, some instructions are 1 address instructions, some instructions are 0 address instructions. Now what I can say how many 2 address instructions, basically how many bit patterns are consumed by 2 address instructions. How many bit patterns are consumed by 2 address instructions? How many bit patterns are consumed by 1 address instruction, and how many bit patterns are consumed by 0 address instruction? If I add all of them, okay, if I add all of them, that will be less than equal to 2 power 16. Yes or no? Is this clear? Now you tell me a very simple point I'm asking you. Now you tell me, if you have two address instruction, consider a particular two address instruction. Okay, consider a particular two address instruction. If I give you a particular two address instruction, I'm giving you, okay, only one, a particular two address instruction I'm giving you, then in that case, what will happen? Because you have a particular instruction, for any particular instruction, what will happen? For any particular instruction, what will happen? Opcode will be fixed, because I am giving you a particular two address instruction. So for this, what will happen? Opcode will be fixed. For any instruction, opcode is always fixed. Yes or no? Whatever instruction I give you, if I give you addition instruction, opcode will be fixed. Subtraction instruction, opcode will be fixed. So for any particular instruction, whatever particular instruction I give you, opcode will be fixed. Now, if I give you a particular instruction, like for example, addition instruction. Let's assume you have addition instruction. Let's assume this is a two address instruction. So you can see opcode is fixed, right? Yes or no? Opcode, this is fixed. This is your opcode. This is the opcode, and this is fixed. You cannot change this, because I am talking about a particular instruction. Remember, okay, I am talking about a particular instruction. A particular instruction I am discussing. So now you can see opcode is fixed. You cannot change anything. But there are two addresses. Yes or no? And what is the size of address? What is the size of operand address? Tell me in this question. Is it given? What is the size of operand address? That is 6 bits. You can see yes or no. Yes or no? 6 bits. 6 bits. So you can easily see that these will be 6 bits. Here you have 6 bits, and here you have 6 bits. Okay, these are the operands. These are the operands. This is operand 1 and this is operand 2. These are the operands. Yes or no? Operand 1 address, operand 2 address. Now you tell me, this addition instruction, you have this addition instruction. Remember, instruction is only one. You have this addition instruction, but this addition instruction will consume how many bit patterns? This addition instruction, please tell me, consumes how many bit patterns? Consumes how many bit patterns? You can easily see it will consume. Remember, here you can put any 6 bits. Here you can put any 6 bits. Yes or no? Here I can put any 6 bits. I can put here. Here I can put any 6 bits. I can put here. Okay. So remember this addition instruction. Please understand, instruction is only one. You have only one instruction, but here you can put any address. Here you can put any address. Any 6-bit address you can put here. This is address, right? Operand 1 address. And this is also address. This is operand 2 address. So what you can do, here you can put any address, and here you can put any address. So this is what I'm saying, that addition instruction will consume how many? It will consume 2 power 6 multiplied by 2 power 6. These many bit patterns. Okay, these many bit patterns will be consumed by addition instruction. Now you tell me one thing. These bit patterns, can I say these are instructions? Like, did I say that these are instructions? Are these instructions? No, these are not instructions. These are the bit patterns consumed by addition instruction. Okay, operation is only one. Please understand, operation is addition. Please understand, your operation is addition. Your operation is this. But you can notice here you can put any 6-bit address. Here you can put any 6-bit address. So depending on what address you put, okay, yes or no, whatever address you can put here, whatever address you want, you can put here. So finally, I can say this operation will consume, this operation will use 2 power, you can see 2 power 6 into 2 power 6. These many bit patterns. These many bit patterns are already used by, okay, these many bit patterns are already used by this instruction. Is this clear? So very simple point. If I give you a particular 2 address instruction, then this will consume 2 power 6 into 2 power 6. These many instructions. Yes, these many bit patterns. So 2 power 6 into 2 power 6. 2 power 6 into 2 power 6. These many bit patterns are consumed by whom? Tell me. These many bit patterns are used by whom? Used by a particular 2 address instruction. 2 address instruction, right? Yes or no? And how many 2 address instruction we want? Tell me. See, a particular 2 address instruction, will consume these many bit patterns. Okay, these many bit patterns will be consumed, will be used by a particular 2 address instruction. And how many 2 address instruction we want? We want 14 double address instructions. Okay, yes or no? So this is what we want. We want total 14 double address instruction. Now you tell me, how many bit patterns will be used by one address instruction? How many bit patterns are used by one address instruction? If you take a particular one address instruction, then what will happen? A particular one address instruction. For example, let's assume you have this inc. Okay, this inc increment. Okay, increment the value of some register. So this is particular one address instruction. Because this is a particular one address instruction, so I can say opcode is fixed. Okay, so I can say what I can say. I can say opcode that is fixed because I am discussing a particular instruction. Okay, so you can see opcode is fixed because I am discussing a particular instruction. So here you can easily see that this opcode, this is your opcode, and that is fixed, and that is fixed. Okay, that is fixed. Now you can see this is one address instruction. Because this is one address instruction, so there is one address only. Okay, so there is one address, yes or no? Because this is one address instruction, so there is only one operand. There is only one operand. That operand address will be here. Only one operand you have, so that is 6 bits. Okay, and remember, the remaining part, that will be opcode. The remaining part will be opcode, yes or no? Okay, so these are the 6 bits for operand. The remaining part is your opcode. Okay, so very simple. So in this, tell me what is the opcode size? What is the opcode size? Let me know. What is the opcode size? That will be 10 bits. That will be 10 bits. Because please understand that you are taking one address instruction, so there is only one address. So you can see 6 bits are taken by the operand address. Okay, these 6 bits, these are taken by operand address. The remaining is your opcode. So opcode size, that will be 10 bits. Okay, anyway, you tell me this increment instruction, this is your operation, increment instruction. Okay, this is one instruction, but you can put any address here. Any 6-bit address you can put here, yes or no? Any 6-bit address I can put here. So tell me, this increment instruction will consume how many bit patterns? Will consume how many bit patterns? It will consume 2 power 6 bit patterns. Okay, so remember, these many bit patterns are consumed by a particular one address instruction. Okay, a particular one address instruction will consume these many. So now you tell me how many we want. Remember, one address instruction, a particular one address instruction will consume these many bit patterns. And how many one address instruction we want? How many we want? We want 127. This is what we want. We want total 127. Okay, so very simple. So these many bit patterns will be consumed by one address instruction. What about zero address instruction? What about zero address instruction? Again, if you take a particular zero address instruction, then what will happen? If you take a particular zero address instruction, if I give you a particular, remember, I am asking a particular zero address instruction. For example, halt, or for example, maybe NOP. Okay, so basically, if you take a particular zero address instruction, then opcode will be fixed, because for any particular instruction, opcode is always fixed. Okay, whenever you have some particular instruction, if I give you one instruction, then opcode is always fixed. Now this is a zero address instruction, so the entire thing is opcode, yes or no? The entire thing is opcode, because this is zero address instruction. In this instruction there is no operand, so the entire thing is opcode. Okay, this entire thing, this is opcode. So what is the opcode size? And this opcode is already fixed. Okay, for this instruction, for this halt instruction, opcode is already fixed. What is the opcode size? What is the opcode size? That will be 16 bits. Yes or no? Because there is no operand in this instruction, there is no operand. So very simple, opcode is fixed. So tell me, this halt instruction will consume how many bit patterns? Tell me, this halt instruction will consume how many bit patterns? This will consume only one bit pattern, yes or no? Because opcode is fixed, the entire instruction is the entire 16 bits, that is fixed. That is fixed, yes or no? Opcode is fixed, and the entire instruction is opcode. Entire instruction, that is opcode. So you can see that is fixed. So I can say that halt instruction consumes only one bit pattern, yes or no? It will consume only one bit pattern. So finally, now you tell me. So you can see a particular zero address instruction will consume only one bit pattern. And how many we want? How many zero address instructions we want? We want total 60. We want total 60. So these many bit patterns will be consumed by zero address instructions. These many bit patterns will be consumed by one address instructions. These many bit patterns will be used by two address instructions. And this total must be less than equal to 2 power 16, because this is the total number of bit patterns possible. Okay, using 16 bits, this is the total number of bit patterns that is possible. Now you tell me, is this equation satisfied or not? This is your equation. Now you just check 14 multiplied by 2 power 12 plus 127 multiplied by 64 plus 60. Is this less than equal to 2 power 16? Please tell me. Let me know. What is this value? Can anyone calculate? You have the calculator. So can you calculate this value? What is this value? 65532. Very good. 65532 less than equal to, what is this value? 64 multiplied by 1024. So tell me, what is this value? This value is 65536. 65536. Is this correct? What I have written? Please tell me. Is this value correct? 65532. Okay, so you can see this equation is satisfied, right? Yes or no? So I can say this equation is satisfied. And because this equation is satisfied, so what I can say? Because this equation is satisfied, so what I can say, is it possible to encode? The answer is yes. Is it possible to encode? The answer is yes. Okay, so this instruction set is possible. This instruction set is possible using expand opcode technique. Okay, is this clear? This instruction set is possible using expand opcode technique. Expand opcode technique. Please tell me, did you understand? Let me know. Is this clear? Okay, so very simple. This instruction, this equation is satisfied. You tell me one more thing, one more observation. So total, these many bit patterns you have, these are the total bit patterns possible, total number of bit patterns possible. Okay, but you want only these. Yes or no? You want only these many patterns. See, these are the total number of bit patterns possible. Okay, and you want only these many bit patterns. This is what you want. So how many bit patterns will be left for future? So how many bit patterns will be left for future? You can see 4 bit patterns you can use for future. 4 bit patterns left for future. Okay, 4 bit patterns are left unused, can be used in future. Okay, okay, unused for future. In future, if you want to use these patterns, you can do that. Yes or no? Okay, after 5 years, if you want to add some more instructions, after 5 years, if you want to add some more zero address instructions, then you can do that. Okay, 4 bit patterns are left unused for future uses. For future uses. Yes or no? Is this clear? So in the future, remember, after 2 years, if you want 4 more zero address instructions, then you can do that. Okay, these 4 bit patterns you can use. Okay, is this clear? Please tell me. So this is your question, and very simple question. So here the answer will be yes. Now tell me one thing, just tell me one thing. This method that we have seen, this bit pattern method, actually this is very quick method. Yes or no? See, just to explain, I've taken so much time because I wanted to explain the concept. What is the concept of bit pattern method? I wanted to explain. I wanted to tell you how to solve this question. Okay, the explanation I told you. So that is the reason a lot of time I took. But remember, this method is actually very easy. Okay, once you have done enough practice, if you remember, in the previous lecture, we have done a lot of practice. Yes or no? I think more than 5-6 standard questions we have solved. And for each question, we have seen this bit pattern method. For every question, we have seen this. So remember, we have done a lot of practice of this method. So this method will not take time. In the GATE exam, what you can do, tell me? What you can do in the GATE exam? How can you do this quickly? Very simple. When you will see this question, you have done enough practice. We have already done enough practice. So when you will see this question, immediately what you will do? You know 16-bit is the instruction size. Okay, yes or no? 16-bit, that is the instruction size. So immediately what you will do? This plus this plus this. So what you will do? Very simple. These are the 2 address instructions. Okay, so how many 2 address instruction I want? I want 14 2 address instructions. And 1 2 address instruction. If I take a particular 2 address instruction, that will consume these many bit patterns. Plus, how many 1 address instruction I want? I want 127 1 address instruction I want. Okay, and if I look at particular 1 address instruction, will consume these many bit patterns. Okay, plus how many 0 address instruction I want? I want 60 0 address instructions. And remember, a particular 0 address instruction will consume 1 bit pattern. Okay, that's it. So tell me, how much time it will take in the GATE exam? Let me know. This bit pattern method, how much time it will take in the GATE exam? Once you have done enough practice, which we have already done, we have done a lot of practice. Now you can solve this question very easily. This equation you can make very easily. Yes or no? I think maybe 10 or 20 seconds it will take. Yes or no? 20 seconds it will take. Within 20 seconds, you can solve this question. Okay. Yes or no? And using the calculator, you can calculate what is this value, you can calculate, and finally you can see the answer. Is this clear? Please tell me, is this understood? Let me know. Okay. Now let's see another method to solve this same question. Can you solve this same question using the another method? There is method number 2. Let's see that. But this was the quick method, remember. Okay, don't use the method number 2 in the GATE exam. In the GATE exam, don't use this method. This method number 2, this you don't use in the GATE exam. What is this method? This method is basically encoding. Yes or no? This method, what is this? This is the encoding method. Or I can say encoding opcodes. Something like this. Okay, encoding instructions method. Okay, encoding instructions method. Basically, in this method, we will actually do the encoding. Okay, so this is the name we can give. So you can see encoding instruction method. Now tell me, in this method, what we will do? Let me know. In this method, what we are going to do? I told you that always start from where? Please tell me. Always start from where? Always start from instructions with smallest opcode. Yes or no? Always start from instructions with the smallest opcode. With the smallest opcode size. Okay, so very simple. So remember, go in the opcode increasing order. Yes or no? Go in the increasing order of opcode size. Increasing order. Go in the increasing order of opcode size. Opcode size. So first you tell me, what is the opcode size here? First you tell me, what is the opcode size here? Let me know. For these instructions, what is the opcode size? Please tell me. For these instructions, what is the opcode size? Double address instructions. For double address instructions, the opcode size is already given 4 bits. Yes or no? That is already given to you. You can see this is a 2 address instruction format. Okay, what is this? This is given to you. This is a 2 address instruction format. This is a 2 address instruction format. So you can see opcode size is already given to you. For single address instruction, what will be the opcode size? What will be the opcode size for these? Please tell me. What will be the opcode size for these? You have single address instructions. Because you have single address instructions, so the opcode size will be 4 plus 6. That will be 10. Yes or no? That will be 10. That will be 10 bits. Okay. And what about the last one? What is the opcode size for the last one? What will be the opcode size for this last one? Please tell me. For these instructions, what will be the opcode size? What is the opcode size? That will be 16 bits. Yes or no? Because there is no address. There is no operand. In these instructions, there is no operand. So the entire instruction is opcode. The entire instruction will be opcode. So 16 bits. So tell me what you will do. Always start from the instructions with the smallest opcode size. So what you will do, you will start with 2 address instructions. Yes or no? First, you will start with 2 address instructions. This is what you will do. First, you will start with the 2 address instructions. How many 2 address instructions we want? Total, how many 2 address instructions we want? We want 14 2 address instructions. Yes or no? Okay, 14 2 address instructions we want. So here what will happen? Because it is a 2 address instruction. Because it is a 2 address instruction, so 6 bits for operand. These 6 bits also for another operand. So these are for operand number 1. These are for operand number 2. And this is your opcode. For opcode, how many bits? Okay, those are 4 bits. Now tell me, using 4 bits, how many patterns are possible? Using 4 bits, how many combinations are possible? 16 combinations are possible. Okay, 0 0 0 0 0 1 and so on. Then 1 1 1 1. 16 combinations are possible. Okay, and how many 2 address instructions I want? I want 14 instructions I want. Okay, for these instructions, for 2 address instruction, the opcode size is 4 bits. You can see using 4 bits, these many combinations are possible. We want total 14 instruction. Then tell me which combinations I will use. Okay, what I can do? 1 1 1 0, 1 1 0 1 and so on, right? Yes or no? So what I can do, I need 14 instructions, right? Yes or no? So what I can do, this is what I can do. These opcodes. Okay, these opcodes, what I can do, tell me. These opcodes I can use for 2 address instructions. Okay, For 2 address instructions, I can use these because total 14 2 address instructions I need. Remember, I want 14 2 address instructions. 14 2 address instructions I want. And remember, for every 2 address instruction, the opcode size is 4 bits. Using 4 bits, these many combinations are possible. From these combinations, what I can do, I can take these 14 combinations. Okay, these 14 combinations I can take. Yes or no? From 0002 to 13. Yes or no? From 0 to 13. So these 14 combinations I can use for 2 address instructions. Tell me what these will be called. The remaining 2 combinations. The remaining 2 combinations. These are free. What we call them? We call them escape opcode. Yes or no? So these are your escape opcode. Now what we will do? Okay, so 2 address instructions are done. We have already created 14 2 address instructions. Now you tell me. Now you will go to 1 address instruction. Now you will go to 1 address instruction. In the 1 address instruction, the size of opcode, what is that? The size of opcode, what is that? Tell me. In the 1 address instruction, this is the opcode. This is the opcode. And the size of opcode, that is 10 bits. Yes or no? Size of opcode, that is 10 bits. And total, how many 1 address instruction I want? I want 127 instructions. Instructions needed. Okay, so these many instructions are needed. Okay, so how to have these many instructions? How to get these many instructions? Very easy. Okay, you already know that for the first 4 bits, you have either this pattern or this pattern. Okay, these 2 patterns. Either you have this pattern for the first 4 bits, either this pattern is there, or you can use this pattern. Yes or no? Either you can use this pattern for the first 4 bits, or you can use this pattern for the first 4 bits. Okay, because these 2 patterns are free. Okay, all the remaining first 4 bits pattern are used by 2 address instruction. Remember, if the first 4 bits are 0000, then that is a 2 address instruction. If the first 4 bits are 0001, then that is a 2 address instruction. So you can see for the first 4 bits, only 2 combinations are free. These are called escape opcode. So you can see in the 1 address instruction, the opcode size will be 10 bits. And for the first 4 bits, these 2 combinations I can use. Okay, now you tell me. Okay, remember, the opcode size is actually 10 bits, right? Yes or no? The opcode size, that is actually 10 bits. So there are 6 more bits here. There are 6 more bits here. This is the opcode size. This entire thing is your opcode. This entire thing is your opcode. Yes or no? And here you have 6-bit operand. Here you have operand, right? Here you have operand. So tell me, now tell me here, how many 1 address instructions I can create? How many 1 address instructions I can create here? The first 4 bits are 1110. Okay, but here these bits are remaining. Okay, these bits are available. These bits are available. So I can create these many opcodes. I can create. Okay, here I can create these many opcodes. Yes or no? 2 power 6 opcodes I can create here. And 2 power 6 opcodes I can create here. Right. Okay. So total I can create 128 opcodes. But how many I want for 1 address instruction? Here I can create 2 power 6 opcodes. Here I can create 2 power 6 opcodes. But total how many I want? Total I want 127. And I can create 128. Yes or no? So remember, I can create 128 opcodes. Okay, for 1 address instructions. For one address instruction, remember what I can do? For 1 address instructions, I can create 120 opcodes. I can create 128 opcodes. Actually, I can create. Okay, I can create, for example, these opcodes 1110, then all 0. Okay, then 1110, then 00001. Okay, and so on, 1110, then 111111. Okay, so 64, these are your 64 plus you can have 1111, then start from 0000. Okay, and so on. You just go like this. Then what you will have? You will have these. You will have, see, 1111, then all ones, and 1111, 11110. Yes or no? Is this clear? So here also, here these are 63. Okay, 64, 63. That is your 127, right? And this is what you need. Okay, so remember, these opcodes will be used by 1 address instructions. So 127 These are the 127 opcodes for one address instructions. Is this clear? For one address instructions. So for one address instructions, these opcodes we are using. These opcodes, they are used by, what are these? These are opcodes used for one address instructions. Is this clear? Used for one address instructions. Okay, please tell me, is this clear? One address instructions. So you can see these are used for one address instructions. Very simple. So what is the escape code? Tell me, what is the escape code? Let me know. What is the escape code? So you can see this is the escape code. Yes or no? This is your escape code. This is the escape opcode. Correct? Is this clear? Because this is free, right? This is free. Okay, so using this, what I can do? Using this, I can create zero address instructions. Now what I will do? I will create zero address instructions. Okay, now I can create zero address instruction. There is no address. So the entire thing is the opcode. Yes or no? The entire thing is opcode. The entire thing is opcode. So opcode size is 16 bits. The entire thing is working as opcode. The entire thing is opcode. So opcode size is 16 bits. Yes or no? Now you can see 16 bits opcode, right? But you already know that the first 10 bits, those are fixed. Yes or no? The first 10 bits, those are already fixed. Okay, these are the first 10 bits. 1111, 11. Okay, so you can see the first 10 bits are already fixed. Okay, is this clear? So how many bits are remaining? 6 bits are remaining. This is your opcode, remember. This is your opcode. Okay, this is your opcode for zero address instruction. So tell me how many zero address instruction you want? Zero address instruction, how many you want? You want total 60. Yes or no? Total 60 instructions we want. Instructions needed. Okay, total 60 instructions we needed. But how many we can create? 60 instructions are needed. Total 60 instructions are needed. Okay, you can see that for the zero address instruction, for a zero address instruction, the first 10 bits are 1111, 1111. Okay, like this. Yes or no? All ones. So first 10 bits are all ones, but still 6 bits are remaining. Yes or no? Still 6 bits are remaining. Yes or no? In the opcode, 16 bits, 6 bits are remaining. So actually I can create how many? Tell me. 2 power 6, that is 64 opcodes possible. Yes or no? 64 opcodes possible, but I need only 60. I only need 60. These many possible. We need 60. We need only 60. We need only 60. So what will happen? So what will happen? Very simple. The remaining 4 will be left unused. Yes or no? Okay, so the remaining 4 can be used in future. Can be used in future. Can be used in future. In future, if you want zero address instruction, if you want more zero address instructions, then the remaining 4 combinations you can use. The remaining 4 opcodes you can use. So please understand. Okay, for zero address instruction, I'm talking about. For zero address instruction, you can easily see these are the opcodes. What are the opcodes? 1111, 111, 111. Okay, so all the way 000 6 zeros. Okay, then the next will be, then the next opcode will be this. Okay, and so on, and so on. Total at the end you will have, this is what you will have at the end. Okay, but remember, total how many we want? Okay, total how many we want? Let me know. Total how many we want? You can see we only want from 0 to I can say 59. Yes or no? From 0 to 59. Tell me what is 59. Please tell me what is 59. What is the binary for 59? Please tell me. Let me know. So you can see for the 59, the binary, what is that? That will be 1. Okay, so basically from here we can just remove 4, right? So that will be 1 1 0 1 1. Is this correct? Yes or no? This is correct, right? I think this is a 1500 because see, this is 63. This is 63. Just remove 4. Just remove 4, right? Yes or no? Okay. So you can easily see these opcodes are used by whom for what? Tell me. So these are the opcodes. These are the opcodes for. These are the opcodes used for zero address instructions. Zero address instructions. Is this clear? Okay. These are the opcodes for zero address instruction. And remember, the remaining four are remaining, right? Yes or no? Okay, so there are 4 remaining. So there are 4 remaining. I think this will be 60. Okay, so just remove 3, right? Yes. Okay, so you can see these four opcodes. Tell me what will happen for these 4 opcodes. These 4 opcodes can be used in future. Can be used in future. Okay, is this clear? You can use them in the future. In future, if you want more zero address instructions, then you can you use these. Okay, so for these 4 opcodes can be used in future. So remember, they are unused. Okay, they are unused. They are unused. If you want, you can use them in the future. In future, if you want more zero address instruction, okay, so you can say in future, if a CPU designer needs if CPU designer needs more zero address instructions, okay, zero address instructions, then they can use these 4 unused opcodes, unused zero address instruction opcodes. Yes or no? These unused opcodes for zero address instructions. For zero address instructions. Okay, so this is the complete explanation. Please tell me. This is the complete explanation. Is this clear? A student is asking, these 4 opcodes has to be only zero address. Yes, these have to be only zero address. Okay, because you already know that these opcodes, they are 16 bits opcodes, right? These four opcodes, they are 16 bits. Yes or no? These 4 opcodes, they are 16 bits opcodes. So they have to be zero address instruction, right? Yes or no? Basically, there is no more what you can do. Okay, you cannot go further. Okay, 0 is the minimum limit. Okay, in an instruction you can have 0 operand, 1 operand, 2 operand, 3 operand. So the minimum is 0 operand, right? Yes or no? Is this clear? So in the future, if you want more zero address instruction, then you can use these opcodes for zero address instruction. Is this clear? Please tell me. Let me know. So this is the complete analysis. Now you tell me, for this question, which method you will actually use in the GATE exam? Tell me. We have seen for the previous question, we have seen total 2 methods. We have seen which method you will use for this GATE 1988 question. This was GATE 1988 question. I want to ask you, if you are in the GATE exam, which method you will use? Which method are you going to use? Method 1 was bit pattern method. That was bit pattern method, right? Okay, so method 1, that is your bit pattern method. And method 2, what is that? Method 2, what is that? That is your, I can say, encoding instructions method. You are encoding various type of instructions method. Various types of instructions. Okay, so you are actually doing the encoding of various types of instructions method. So tell me, which method you will use? Just tell me. Now let me tell you something very interesting. This method 1 is the best method, right? This is the best and quickest. Okay, but this is what majority of the students they will use. Okay, actually, I have seen this from my experience. I have seen this. Majority of the students, they will use this method number 2. Okay, but actually the best and quickest method, that is the method number 1. But I have seen this. This is from my experience that I have seen in the last 5 or 6 years. I have seen that many students, majority of the GATE students, okay, majority of the GATE aspirants who don't study from standard resources, majority of the GATE aspirants who don't follow standard resources or who don't follow GoClasses, basically majority of them, they use this method. Okay, but did you notice for the same question, we have solved the question using method number 1 also, using method number 2 also. Please tell me, if you use method number 1 and if someone else is using method number 2, then how much difference will be there? You can use this method number 1 and you can solve this question within 1 minute. You can solve this question within 1 minute. But if you use this method, if you use this method number 2, it will take maybe 3, 4, 5 minutes. Yes or no? Yes or no? More than 5 minutes it can take. So you can see in the GATE exam, in those 3 hours, you should follow the quickest approach, the best and quickest approach. So remember this method number 1. This method is the quickest and best method. But majority of the students, majority of the GATE aspirants, they follow this method number 2. But this is a nonsense method. Of course, this is correct method. Method number 2 is also correct. Method number 1 is also correct. But this method number 2 for an objective exam, okay, in the GATE exam, this method number 2, this is nonsense method. Okay, if you apply this method number 2 in the GATE exam for expand opcode technique, it will take a lot of time. Okay, it will take a lot of time. But you can save a lot of time. You can save using this method number 1, and this is very good also. Okay, this is very, so I can say this is best and quickest method. Is this clear? Now let's move on. Now let's solve this question. This is GATE 1992 question. Tell me the answer. For this question, let's solve it. We will apply the method number 1. Okay, let's solve this question using method number 1. That is your bit pattern method. So let's solve this question using bit pattern method. What this question is saying, this is GATE 1992 question on the expand opcode technique. This is saying that in an 11-bit computer instruction format, instruction size is 11-bit, the size of address field is 4 bits, the computer is using expand opcode technique and has 5 2-address instructions, has 32 1-address instructions, the number of 0-address instructions it can support. The number of 0-address instructions it can support. So let's assume number of 0-address instructions it can support. Let's assume that is n. Okay, yes or no? Assume that is n. Is this clear? What you do, you assume this value is n. Okay, so assume n 0-address instructions it can support. Now tell me, just apply the method number 1. Just apply your method number 1. What is that? That is your bit pattern method. Just apply that. Just apply bit pattern method. In the bit pattern method, tell me what will happen. Very simple method. This is the simplest method. In this bit pattern method, what you will do? Instruction size is 11 bits. So tell me how many total bit patterns possible? Total number of bit patterns possible. Tell me. Instruction size is 11 bits. So how many total bit patterns are possible? Total number of bit patterns possible. What is that? Total number of bit patterns possible. That is 2 power 11. Yes or no? 2 power 11. These many bit patterns are possible. Remember, these many bit patterns are possible. Yes or no? Now you can see every instruction has 11 bits. Every instruction that has 11 bits. So I can say these many bit patterns are possible. Okay. Out of these bit patterns, from these bit patterns, some instructions will have some will be 3-address instruction, some will be 2-address instruction, some will be 1-address instruction, some will be 0-address instruction. Yes or no? See, very simple point. I'm telling you, every instruction, you take 2-address instruction, 1-address instruction, 0-address instruction, every type of instruction that has 11 bits. Using 11 bits, these many bit patterns you can create. These many bit patterns I can create. Now you can see from these bit patterns, some will be 2-address instruction, some will be used by some of them will be used by 2-address instructions. Some of these bit patterns will be used by 1-address instructions. Some of these bit patterns will be used by 0-address instructions. Yes or no? So you tell me how many bit patterns are used by 2-address instructions? Let me know. How many bit patterns are used by 2-address instructions? You can see 5 2-address instructions you have, and every 2-address instruction will consume how many bit patterns? Every 2-address instruction, the address field is 4 bits. So every 2-address instruction will consume these many bit patterns. Okay, yes or no? So you can easily see that these many 2-address instructions you have, every 2-address instruction will consume these many bit patterns. Yes or no? Plus. Okay, so remember, a particular These are the bit patterns, number of bit patterns consumed by a particular to address instruction. What is this? So please understand what is this. This is number of bit patterns. This is the number of bit patterns consumed by a particular to address instruction. Okay, a particular to address instruction. So very simple. Any particular to address instruction, if you take a particular to address instruction, if you take, then that will consume these many bit patterns. And total, how many to address instruction we have? 5. Very simple. Plus what to do? Plus what to do? How many bit patterns will be consumed by one address instructions? How many bit patterns will be consumed by one address instruction? Total, these many one address instruction we have. Okay, and every one address instruction will consume these many bit patterns. Yes or no? These many bit patterns. These many bit patterns. Okay, so what I can say 32 multiplied by 2 power 4 plus what to do? Now you can see how many zero address instructions we have. Tell me how many zero address instructions we have, that we have assumed n. Yes or no? N multiplied by a particular zero address instruction will consume how many bit pattern? A particular zero address instruction will consume how many bit pattern? 1, right? Yes or no? So very simple. This should be less than equal to this. This is the equation, because these are the total number of bit patterns possible. So now can you solve this equation? What will be the answer? So tell me, 5 into 2 to the power 8, that is your 256, plus 32 multiplied by 2 power 4, that is your 512, plus n, this is less than equal to 2096, right? Yes or no? So tell me, what is the value of n? Here, from here, what is the value of n that you can find? N will be less than equal to what? Please tell me, n will be less than equal to what? N will be less than equal to 256. So tell me maximum, what is the maximum value of n? Okay, what is the maximum value of n? That is 256. So I can say that, what I can say from here, I can say that we can support, okay, maximum 256 zero address instruction. Yes or no? 256 zero address instructions. Is this clear? Please tell me, is this point clear? So for this question, the answer will be what? Let me know. The answer is going to be 256. Okay, for this question, for this GATE 1992 question, the answer will be 256. You tell me one thing. Is this method beautiful or not? This bit pattern method. Yes or no? This bit pattern method, this is very quick method. Yes or no? This is the best and quick method. I told you this is the best and quickest method. Can you solve the same question using the other method? Can you solve the same question by doing the encoding? Can you solve? Please tell me. Can you do that? So take that as a homework. Okay, take that as a homework. So please solve the same question. The same question you try, you solve using the method number 2. Is this clear? Please tell me. We have done this question using the bit pattern method. So method number 1, using method number 1, we have already solved this question. The method number 2, can you apply? Please tell me. Let me know. The method number 2, can you apply and can you solve this question? Let me know. Okay, so very simple. Is this clear? Please tell me. Shivam is saying the meme, so beautiful, so elegant, just looking like a wow. Yes, indeed. This bit pattern method, let me tell you, this is like a wow. Okay, this is a very good method. This is best and quickest method. Okay, but still remember, in the GATE exam, majority of the GATE aspirants who do not study from standard resources, who don't study from GoClasses, they will use the other method. Method number 2. They will do the encoding. First, they will take 2 address instruction, then they will take 1 address instruction, then they will take 0 address instruction. Okay, so that method they will apply. And let me tell you, that method is dumb. Okay, in the GATE exam, that method will take a lot of time. That method is going to take a lot of time. Is this clear? So you can solve all the questions based on expand opcode technique, all these questions you can solve using two methods. We have seen two methods. Method number one, that is bit pattern method, and method number two, that is encoding of instructions. Okay, that also we have seen. So remember, there are two methods to solve questions based on expand opcode technique. Both the method we have seen. We have done a lot of practice, so you are confident. Okay, you can use any method. Method number one, method number two, you can use any method. But remember, method number one, this bit pattern method, this is the best. This is the quickest. Okay, let's move on now. Now let's solve this question. Let's solve this GATE 2018 question. This is GATE 2018 question. A processor has 16 integer registers. These are the integer registers, and there are 64 floating point registers. It has 2-byte instruction format. Okay, every instruction has 2 bytes. Next, there are 4 categories of instructions: type 1, type 2, type 3, type 4. Type 1 category consists of 4 instructions, each with 3 integer register operands. Type 2 category consists 8 instructions, each with 2 floating point register operands. Type 3 category consists of 14 instructions, each with 1 integer register operand and 1 floating point register operand. Type 4 category consists n instructions, each with a floating point register operand. The maximum value of n. Tell me which method you will apply. Please tell me. To solve this question, which method you will apply? This is expand opcode technique based question. So tell me, which method are you going to apply? Bit pattern method. Okay, so just try that. Yes or no? You can solve this question very quickly. Just apply the bit pattern method. Just apply the bit pattern method. So tell me, if you apply the bit pattern method, what will be the answer? Very simple. First of all, you tell me what is the instruction size. What is the instruction size? 2 bytes. Yes or no? The instruction size. The instruction size, that is 2 bytes. So that is your 16 bits. Okay. So using 16 bits, how many patterns are possible? How many bit patterns are possible total using 16 bits? These many bit patterns are possible. Yes or no? 2 power 16. These many bit patterns possible. These many bit patterns possible. These are the total. Yes or no? Bit patterns total. These many bit patterns possible. Okay. So very simple point. Remember, all the instructions, they have 16 bits. All the instructions, they have fixed length. Every instruction uses 16 bits. Okay. The length of every instruction, the length of every type of instruction is 16 bits. Now, using 16 bits, how many bit patterns you can create? You can create 2 power 16 bit patterns you can create. Now, from these bit patterns, remember, some will be used by type 1 instruction. Okay. These many bit patterns are possible using 16 bits. Now, from these bit patterns, some of them will be used by type 1 instructions. Some of them will be used by type 2 instructions. Some of them will be used by type 3 instructions. And some of them will be used by type 4 instructions. Okay. So you tell me, how many bit patterns are used by type 1 instruction? Please tell me. How many bit patterns used by type 1 instructions? How many bit patterns used by type 1 instruction? Please tell me. Let me know. I'm asking, how many bit patterns are used by type 1 instructions? So tell me. Very simple. Total, how many type 1 instructions you have? Total how many? You can see type 1 category consists of 4 instructions. There are total 4 instructions. Okay, one instruction will take how many bit patterns? Okay, these many type 1 instructions you have. Total 4 type 1 instruction you have. One type 1 instruction will take how many bit patterns? If I give you a particular type 1 instruction, if I give you a single type 1 instruction, then how many bit patterns it will consume? So you can easily see every type 1 instruction has 3 integer operands. Yes or no? 3 integer operands. Remember, you have 16 integer operands. So how many bits for integer operands? How many bits for integer register? Tell me. Integer register address bits. That will be 4 bits. Yes or no? And what about floating? What about floating register address bits? Those will be 6 bits. Okay, so now you tell me how many type 1 instructions, are there? Total 4. So total 4 type 1 instructions are there. If I give you a particular type 1 instruction, then that will consume how many? This is your type 1 instruction. This is your type 1 instruction. There is opcode, and then there are integer registers. Integer register R1, integer register R2, integer register R3. Yes or no? Here you have how many? 4 bits. Okay, here you have how many? 4 bits. Here you have how many? 4 bits. Now remember, if I ask you a particular, okay, a particular type 1 instruction. Okay, if I ask you a particular type 1 instruction, then opcode will be fixed. Okay, because I am talking about a particular type 1 instruction. So this opcode, this is fixed. This is fixed. So finally, what will happen here? How many bit patterns are used? So here, tell me how many bit patterns are used. Let me know. So here I can say that 2 power 4, because here you can put any 4 bits. Here you can put any 4 bits. Here you can put any 4 bits. Means here you can put any integer register. Here you can put any integer register address. Here also you can put any integer register address. So I can say, if I give you a particular type 1 instruction, then this opcode will be fixed, because for every particular instruction, opcode is always fixed. Okay, so how many bit patterns will be used? So you can see 2 power 4 into 2 power 4 into 2 power 4. These many bit patterns used by a particular type 1 instruction. Yes or no? A particular type 1 instruction. Okay, is this clear? By a particular type 1 instruction. If I give you a particular type 1 instruction, then these many bit patterns will be used. Okay, and total how many we have? Total these many 4 type 1 instructions we have. Or every type 1 instruction will consume these many bit patterns. Plus, what about type 2 instructions? Please tell me. What about type 2 instructions? How many bit patterns are used by type 2 instructions? Please tell me. Okay, let me know. So again, you can see in the type 2 category, you have a total 8 instructions. First of all, total you have 8 instructions multiplied by, you can see each with 2 floating point register operand. Okay, each with 2 floating point register operand. So you can see every type 2 instruction will consume how many bit patterns? So that will be 2 power 6 into 2 power 6. Yes or no? Is this clear? Because every type 2 operand, every type 2 category instruction has 2 floating point register operand. So you can see, if I give you a particular type 2 instruction, then that will consume these many bit patterns. Plus, what about type 3? Please tell me, what about type 3? Let me know. What about type 3 bit patterns? Please tell me. What about type 3 bit patterns? You can see how many type 3 instructions we have? 14. You have 14 type 3 instructions. Now you can see a particular type 3 instruction has 1 integer register operand, 1 floating point register operand. So tell me, a particular type 3 instruction will consume how many bit patterns? Very simple. 2 power 4 multiplied by 2 power 6. Yes or no? Very good, very good, very good. Everyone is giving correct answer. Every one of you is giving correct answer. Very good. Okay, type 4 bit patterns. How many bit patterns are consumed by type 4? How many bit patterns are consumed by type 4 instructions? Please tell me. You can see total these many type 4 instructions we have. Total these many remember these many n is the total number of type 4 instructions. Okay, if you see a particular type 4 instruction that will consume how many bit patterns? You can see every type 4 instruction has 1 floating point register operand. So if you see a particular type 4 instruction that will consume 2 power 6 bit patterns, yes or no? 2 power 6 bit patterns will be consumed by a particular type 4 instruction. Okay, so very simple. So this is the answer. So tell me, can you take your calculator and let me know? This will become how much? 2 power 14, yes or no? This will become 2 power 14. So it will be 2 power 14 plus plus how much? This will become 2 power 15. Yes or no? This will become 2 power 15 plus how much this will become? 14 into 2 power 10 plus n into 2 power 6, right? N into 2 power 6. And this entire value is less than equal to 2 power 16. Now, can you tell me what is the value of n here? You just calculate and tell me what is n less than equal to. What is n less than equal to? Please tell me. N less than equal to 32. N is less than equal to 32. So what is the maximum value of n? N less than equal to 32. So what is the maximum value of n? That will be 32. So the answer will be what? Answer will be the maximum value of n will be 32. Okay. You just tell me one thing. This question based on expand opcode technique. This is GATE 2018 question. Okay. We have solved it using bit pattern method. Okay. This is the method we have applied. Bit pattern method we have applied. We have solved this question. If you solve this question in the GATE exam using the second method, how much time it will take? Just tell me. If you solve this question in the GATE exam using the method number 2, then how much time it will take? It will take a lot of time, remember. Maybe 5 or 10 minutes it will take. But if you use the bit pattern method, it will take maybe 1 or 2 minutes. Okay, so remember, the same question you can solve using 2 methods. The bit pattern method we have already seen. Okay, using the bit pattern method, I have already given you the solution. And can you apply the second method? You know, encoding the instruction method. Please tell me, can you actually give the encoding of these instructions? Means actually give me the encoding of these instructions, type 1, type 2, type 3, type 4. Okay, so can you apply that method? Can I give you that method as a homework? Please tell me. For this question, the method number 2, can you apply as a homework? Let me know. We have already done a lot of practice in our previous lecture, and also in this lecture, we have done a lot of practice we have done. So I have full confidence on you, you can do it. Okay, so please take the method number 2 for the same question as a homework. Okay, let's move on. Let's solve this question. So let's solve this GATE 2020 question. A processor has 64 registers. So tell me, for register address, how many bits you need? For register address, how many bits you need? For register address, how many bits you need? Total 64 registers are there. So for register address, you need total 6 bits. Yes or no? Very simple. The question is saying 16-bit instruction format you have. Every instruction has 16 bits. It has 2 type of instructions. There are 2 type of instruction, I type, R type. There are 2 type of instruction. Each I type instruction, what this question is saying, every I type instruction contains opcode, register name, 4-bit immediate value. Okay, so remember, if you look at I type instruction format, what is that? I type instruction format is something like this. There is opcode. Okay, there will be opcode. Here you have opcode. Then there is a register name. Then there is a register. Okay, maybe R1. So there is register. Then you have 4-bit immediate value. Means there are 4 bits. There are 4 bits for some value in this instruction. Okay, some value here. Here you have some value. Okay, immediate value, maybe some value you have. Basically, this is some value within the instruction. 4-bit immediate value you have. So within the instruction, you have these 4 bits immediate value. Okay. R type instruction, what that has opcode. There is opcode and 2 register names. If there are 8 distinct I type opcode, okay, 8 distinct I type opcodes are there, then the maximum number of distinct R type opcodes, what that will be? So let's assume that will be n. Let's assume that will be n. So remember, how many I type instructions are there? How many I type instructions are there? 8. Yes or no? Total 8 distinct I type opcodes are there. That means I type instruction, how many you have? Total 8. And the question is asking maximum number of distinct R type opcodes, means how many R type instructions are there in your instruction set? In your instruction set, how many R type instructions are there? So let's assume that is n. So just apply the bit pattern method. Yes or no? Just apply the bit pattern method. You can easily solve this question using the bit pattern method. So what will happen? What will be the answer? Please tell me. You can easily see the instruction format, that is 16 bits. So every instruction has 16 bits. So using 16 bits, 2 power 16 bit patterns are possible. So these many total bit patterns are possible. You have these many bit patterns. Now you can see, remember, every instruction, I type instruction, R type instruction, whatever instruction you take, both these instructions, what they will do, they will use 16-bit instructions. Okay, so remember, every I type instruction, every R type instruction, the instruction length is 16 bits. So using 16 bits, these many bit patterns are possible. Now, some of these bit patterns will be used by I type instruction. Okay, and similarly, some of these bit patterns will be used by R type instructions. Okay, so tell me, how many bit patterns will be used by I type instructions? How many bit patterns used by I type instructions? So you just tell me how many bit patterns are there? How many bit patterns are there used by I type instructions? I type instructions. Okay. Plus, you tell me how many bit patterns are consumed by R type instructions. How many bit patterns are used by R type instructions? Okay. So you tell me, very simple. If you have a particular I type instruction, look at a particular I type instruction. Okay. Let's look at a particular instruction of I type. Okay. So I type instruction. Let's look at a particular instruction. Let's look at a particular I type instruction. Okay. So let's assume you have a particular I type instruction you have. Now, in this particular instruction, what will happen? Because you have a particular instruction, so opcode will be fixed. So opcode will be what? Opcode will be fixed. Agree with me? Okay. So remember, here opcode is already fixed. This opcode, because I'm discussing a particular instruction I'm discussing. So that is the reason this opcode that will be fixed. That is already fixed. Okay. What else you have? Here you have a register name, and here you have 4 bits for immediate value. Okay. And for register, you have 6 bits. For register name, you need total 6 bits. So you tell me a very simple point. This opcode is fixed. This particular I type instruction, example, let's assume that is ADD, addition. Okay, let's assume that is addition. That is your addition instruction. So you tell me, this particular instruction will consume how many bit patterns? Let me know how many bit patterns will be consumed. So you can see here you can put any 6 bits, and here you can put any 4-bit value. Here I can put any 6-bit value. Here I can put any 4-bit value. Any 4-bit immediate value I can put here. Any 6-bit register address I can put here. So finally I can say that 2 power 6 multiplied by 2 power 4. These many bit patterns consumed or not? These many bit patterns used. Okay, these many bit patterns are used by a particular I type instruction. If you have a particular I type instruction, then these many bit patterns are consumed. Okay, so remember, 2 power 4 into 2 power 6, these many bit patterns are consumed. And how many I type instructions we have? A particular I type instruction will consume these many bit patterns. Okay, so what is this? These are the number of bit patterns consumed by, this is the number of bit patterns used by a particular I type instruction. A particular I type instruction. Okay, is this clear? So tell me, how many I type instruction we have actually? How many we have? You can see 8 distinct I type opcodes are there. 8 distinct I type opcodes are there. So 8. Okay, multiplied by how many bit patterns will be used by R type instructions? We are assuming these many R type instructions you have. Okay, assume these many R type instructions you have, because we are assuming maximum number of distinct R type opcodes. So I'm assuming n. So total these many R type instructions you have. Every R type instruction will consume how many bit patterns? Look at every R type instruction. Every R type instruction has opcode and 2 register names. So remember, every R type instruction will consume 2 power 6 into 2 power 6 these many bit patterns. So this is your equation. Now you can solve this equation and tell me the answer. So tell me what is the answer. Here you have 2 power 13 plus n multiplied by 2 power 12 that is less than equal to 2 power 16. Okay, so what you can do, you can take 2 power 12 common. You can take 2 power 12 out. Okay, so what you will get? You will get 2 plus, you can take 2 power 12 out. So you will get 2 plus n, that is less than equal to 2 power 16. So from here, what will happen? 2 plus n, that is less than equal to 2 power 4. Okay, you can divide, right? So finally, I can say that n is less than equal to 16 minus 2. N is less than equal to 14. So what is the maximum value of n? What is the maximum value of n? N is less than equal to 14. So what is the maximum value of n? That will be 14, right? Yes or no? So the maximum value, the question is already asking the maximum value of n, that will be 14. So for this question, the answer will be 14. Is this clear? So very easily you can solve this question using bit pattern method. Very easily, very quickly. Yes or no? So tell me, are you confident in the bit pattern method? In the GATE exam, whatever question comes based on expand opcode technique, let me tell you, in the GATE exam, every question based on expand opcode technique we have solved. This GATE 2020 question we have already done. Okay. Each and every GATE exam question is over. That's it. That's it. Each and every GATE exam question based on expand opcode technique we have done, we have solved. So now you tell me, are you confident in the expand opcode technique? In the GATE exam, whatever question comes, you can use the bit pattern method, yes or no? But there are two methods to solve the same question. The same question you can solve using two methods. We have done enough practice of both the methods. A lot of practice we have done. In the previous lecture we have done, and also in this lecture we have done. Are you confident? Please tell me. This bit pattern method, this has become your favorite or not? Very simple method, right? Yes or no? Whatever question comes, you can easily solve. Any question you can easily solve using bit pattern method. So remember, in the GATE exam, if any question comes based on expand opcode technique, just apply the bit pattern method and that's it. Okay, very quickly you can solve the question. Very quickly you can get the answer. Okay, now let's solve this question also. Let's quickly solve this question also. This is a standard question from a standard university. This instruction format is given to you for a 3 address instruction. Remember, every instruction has 22 bits. So this is the length of the instruction, that is 22 bits. Okay, and this is the instruction format for 3 address instruction. Now the question is saying design and expand opcode to allow all the following to be encoded in 22-bit instructions. This is what we want. What we want 12 instructions with three 6-bit addresses, 120 instructions with 1 6-bit addresses, and 100 instructions with no addresses. First of all, you tell me, is this possible or not? Okay, first you tell me the answer. Is this possible or not? So if I ask you, is this possible or not? What method you will apply? Is this possible or not? This is my first question. First of all, is it possible or not? So which method you will apply? Just apply the bit pattern method. Okay, just apply bit pattern method. So here what will happen? Very simple. The instruction size is already given to you. That is 22 bits. So how many bit patterns are there? 2 power 22. These many bit patterns are there. How many bit patterns are used by 3 address instructions? By 3 address instructions. So you can see these many 3 address instructions I want. And remember, every 3 address instruction has 3 6-bit addresses. So I can say every 3 address instruction will consume these many bit patterns, right? Okay, this value. So these are the bit patterns consumed by, please understand, these are the bit patterns used by 3 address instruction, 3 address instructions. Okay, now tell me, how many bit patterns will be used by 1 address instructions? How many bit patterns? How many bit patterns will be used by 1 address instruction? This is 1 address instruction. So total 121 address instruction you want. These many 1 address instruction you want. Okay, every 1 address instruction has 6-bit address. So that will be like 2 power 6 plus. How many bit patterns used by 0 address instruction? So that will be 100 multiplied by 1. Okay, so can you take your calculator and tell me, is this equation satisfied? Is this equation satisfied or not? This equation, is it satisfied or not? Yes, this equation is satisfied, right? Okay, so this equation satisfied. This equation is satisfied. So yes, it is possible. So this instruction set is possible, right? So this instruction set possible. Okay, this instruction set is possible. But in the question, he is asking us to design the actual encoding. Yes or no? We have to design the actual expand opcoding. Is this clear? That is what we have to design. We have to design the expand opcode. We have to give the opcodes. Okay, so that is what we have to design. So tell me, in which order you will go? In which order you will go? You will go in the opcode order. Yes or no? You will start with the smallest instruction with smallest opcode. Here, what is the opcode size? Here, what is the opcode size? 3 address instruction. You have 3 address instruction. 6-bit, 3 6-bit addresses. So what is the opcode size? If you have 3 6-bit addresses, then the opcode size will be 4 bits. Okay, opcode size will be 4 bits. Yes or no? Because this is the instruction size. You have 3 6-bit addresses, 3 6-bit addresses, so opcode size will be 4 bits. For this, what will be the opcode size? For this, what will be the opcode size? Please tell me. 1 6-bit address. So what is the opcode size? That will be 16 bits. And for these, what is the opcode size? What is the opcode size? That will be 22 bits. Okay, so always start from instructions with the smallest opcode. Okay, always start here. Always start from instructions with the smallest opcode. So start with 3 address instruction. Start with 3 address instructions. Okay, in the 3 address instructions, you can easily see the opcode size. This is opcode size, that is 4 bits. Using 4 bits, how many combinations are possible? Using 4 bits, total 16 combinations are possible. Yes or no? From these 16 combinations, how many 3 address instructions I want? I want 12. Yes or no? I want 12. 12 3 address instructions I want. So remember, from here to 11, from here to 1011. Okay, these I can use. What I can do? These I can use for, oh, these are the opcodes. Please understand. These are the opcodes for 3 address instruction. Okay, because I need, remember, I need total 12 instructions. We need total 12 instructions needed. So you can see these are the 12 opcodes you can use. These are the opcodes you can use for 3 address instructions. Okay, what are the escape opcodes? Please tell me. What are the escape opcodes? So these are the escape opcodes. How many? These are the escape opcodes. These four escape opcodes. Okay, clear? Please tell me. So these are the 4 escape opcodes. Very simple. Okay, now what you will do? Now you will design 2 address instruction. Now you will design 2 address instruction. In a 2 address instruction, what will happen? In a 2 address instruction, so 6 bits, and your opcode. This is your opcode, right? This entire thing is your opcode. This entire thing is your opcode. So what is the opcode size? Opcode size. Sorry, not 2 address, 1 address. Directly we have 1 address, because you can see we have 3 address and directly 1 address. We don't have 2 address instructions. Okay, we do not have 2 address instructions. We directly have 1 address instructions. We directly have 1 address instructions. We do not have 2 address instructions. Is this clear? Okay, so remember, we directly have 1 address instructions. So these are the 6 bits. So opcode size, that is 16 bits. Okay, but here you can notice that already what are the first 4 bits? What are the first 4 bits possible? What are the first 4 bits possible? See, look at this opcode. If you look at this opcode, in this opcode, you tell me what are the first 4 bits possible. This opcode will be like this. The first 4 bits can be these. Okay, and then there will be 12 bits remaining, right? Yes or no? Can you notice there will be 12 bits remaining? Okay, yes or no? Okay, these are 12 bits remaining. So similarly, and so on. 1101, then there will be 12 bits remaining. Then 1110, 12 bits remaining. Then 1111, 12 bits remaining. Is this clear? Okay, is this clear? Please tell me. So how many one address instructions we need? We need 120, right? Okay, we need 120. We need 120 instructions we needed. So how can I get 120 instructions? 120 instructions actually I can get here only. Yes or no? I can get here only. Here only I can get. Here only I can get basically 120 instructions I can get here only, right? Yes or no? Is this clear? Because here 2 power 12, these many opcodes you can create. These many opcodes. Okay, these many opcodes you can create. But out of these, I can use 120. Okay, 120 used for 2 address instructions. 2 address instructions. Sorry, 1 address instructions. Okay, 1 address instructions. Is this clear? So very simple. So basically, these you don't even have to use. These you don't even have to use. These are like, I can say unused. Can be used in future. Can be used in future, right? Yes or no? You can use them in the future. They are actually unused. Okay. Here only you can create everything, whatever you want. And finally, zero address instruction. Finally, zero address instruction. In the zero address instruction, what will happen? How many you need? First of all, you tell me. You need 100, right? Okay, 100 zero address instructions I want. 100 instructions needed. 100 instructions needed. Actually, that you can get from here only. Okay, that you can get from here only. So anyway, you can do that, right? Okay, so 100 instructions are needed. So what you can do in the zero address instruction, the entire thing is opcode. The entire thing is opcode, right? Okay, here the entire thing is opcode. So opcode size is actually 16 bits. Okay, so what you can do, you can just, for example, what you can do, I'm telling you, see, you want in the one address instruction, you want 120, right? Okay, let's focus on one address instruction first. In the one address instruction, I need total 120, right? 120 instructions needed. 120 instructions needed. Now, what I told you that this combination itself can give you everything. Okay, this combination like 1100. Okay, and then 120 instructions here only you can get. Okay, 120 instructions here only you can get. Actually, 16 bits are there. Actually, there are 16 bits. So what you, okay, how many you need? You need only 120. You need only 120. So last 7 bits actually, last 7 bits, they will give you everything, whatever you want. Last 7 bits. How many remaining bits are there? So you can see total 16, 16 minus these 4. So that is 12 minus these 7. So 5 bits, right? Yes or no? Okay, so 5 bits. So what you can do? 0, 0, 0, 0. Okay, now you can see one thing you can see. Actually, these from here you can take 120 instructions. Yes or no? From here you can create 120 opcodes for one address instructions. Okay, one address instructions. Very simple. Okay, a lot will be remaining. Okay, yes or no? Everything else will be actually remaining. Everything else will be remaining. For example, if you have 1100, everything else will be actually remaining. For example, if I put 0001, if I put 0010, and so on, and so on, 11111, and so on. All these are also unused. Or these are also unused. These are also unused. Basically, a lot of combinations will be unused. Are you getting my point? In this question, a lot of combinations are actually unused. You can use them in future. Okay, for future uses, you can use them in future, but a lot of combinations are actually unused. Now you can create zero address. You need only 100 instructions. Okay, very easily you can create. What you can do, maybe one of them you can get, maybe one of them you can take, maybe you can take this. Okay, 100, maybe you can take this 1100, and then maybe you can take this last one you can take. Okay, maybe this last one you can take. So you can take 1111. Okay, and then remember, only 100 you need. You need only 100, right? Opcode size is actually 22 bits because the complete thing is opcode. Okay, in the zero address instruction, the complete instruction is opcode, so 22 bits. Okay, so what you can do, you can just take maybe, okay, just take basically 100 for the 100 instruction, just leave the last 7 bits. Okay, just leave the last 7 bits. The last 7 bits you leave, and the remaining, how many bits are remaining? 22 minus 7, that is 15, right? Yes or no? So 4, 4, 3, that is 11, 12, 13, 14, 15. Yeah, okay. So from here you can create 100. From here you can create 100 opcodes. 100 opcodes. What you can do, from here you can create 100 opcodes for zero address instructions. Zero address instructions. Okay, so anyway, so this method you don't have to apply in the GATE exam, right? Yes or no? Is this clear? For the GATE exam, what you will do? Tell me. In the GATE exam, if this question comes, what you will do? If this question comes in the GATE exam, just apply the bit pattern method. That is very easy, very quick. Okay, just apply the bit pattern method. You can do this very easily. Within 1 minute, within 30 seconds, you can solve the question. Okay, so just apply that method. That bit pattern method, just apply. But anyway, for practice, this is what I have given to you. The actual encoding I have designed. Yes or no? I am designing the actual encoding using expand opcode technique. Okay, we started with 3 address instructions, then 1 address instruction, then 0 address instruction. Okay, so that design I have done. Okay, this is the last question in our today's session. In this session, this is the last question. I just want to ask you, is it possible or not? Using the bit pattern method, you just tell me, is it possible or not? Okay, remember, is this possible or not? I am just asking you, is it possible or not? Means a CPU is designed. You are designing a CPU to have the following instructions. This is the instruction set you want. 3 2 address instructions, 31 address instructions, 45 0 address instructions. The machine code length for each instruction is 12 bits. This is the instruction length. Okay, for each instruction, that is 12 bits. Each address field is 5 bits. Every address field has 5 bits. What else? You can see, using the expand opcode technique, list the machine codes for above instructions and determine whether this design is possible or not. Okay, you tell me, is this possible or not? This is my question. That's it. You just tell me, is this possible or not? Let me know. Is it possible? Just use the bit pattern method and tell me, is this possible? So you can see the length of every instruction, that is 12 bits. So using 12 bits, 2 power 12, these many bit patterns are possible. Out of these bit patterns, some bit patterns will be used by 2 address instructions. Some of these bit patterns will be used by 1 address instructions, and some of them will be used by 0 address instructions. So tell me, how many bit patterns will be used by 2 address instructions? Let me know. 3 2 address instructions you have. 3 2 address instructions you have. 2 address instructions you have. So a particular 2 address instruction will consume how many bit patterns? You can easily see every address has 5 bits. So a particular 2 address instruction will consume 2 power 5 into 2 power 5. These many bit patterns. Okay, plus what you will do, plus 30 1 address instructions, 30 these many instructions, 1 address instructions. So a particular 1 address instruction will consume 2 power 5 bit patterns plus 45 0 address instructions. Your 45 0 address instruction, a particular 0 address instruction will consume only 1 bit pattern, right? Yes or no? So this is the point. So tell me, is this equation satisfied or not? Is this equation, look at this equation and tell me, is this satisfied or not? So it will be like 4077 less than equal to 4096. Okay, this is satisfied, right? This is satisfied. So possible. So possible. So the answer is yes, it is possible. Okay, this is a possible. Is this possible or not? Yes, possible. So the answer will be yes, possible. Okay, you can say yes, possible. Is this clear? Very simple. Okay, one more observation can you make? One more observation can you make, that these many bit patterns we want, these many bit patterns we can have, total these many bit patterns we can have. Okay, total these many bit patterns are possible, but we want only these many bit patterns. So I can say some bit patterns will be unused. Yes or no? Some bit patterns will be unused. Okay, unused. If I ask you how many bit patterns will be unused, how many? If the question asks you how many bit patterns will be unused, then what will be the answer? How many unused bit patterns? That will be 19. Okay, just from here, just remove this. Okay, so that will be 19. Is this clear? So very simple. So remember some bit patterns, there are some bit patterns will be unused. How many? That will be 19. Okay, so this is your expand opcode technique. All the questions we have done, that's it. Okay, so this is your lecture. Please tell me, got it? Let me know. Did you understand everything? Expand opcode technique in the GATE exam, many questions have come from this technique. Okay, from this expand opcode technique. You can see in GATE 2018 there is a question, in 2020 there is a question, 2020, 2018, and there are some more questions in the GATE exam from expand opcode technique. So that is what we have seen. We have solved each and every GATE exam questions based on this expand opcode technique, and also we have seen the concept. Okay, I told you multiple methods to solve any question based on expand opcode technique. The best method is bit pattern method. That also we have seen, and we have done a lot of practice. In the last class, we have done a lot of practice. Standard resources questions we have solved, and in this lecture we have done all the GATE exam questions we have solved. Okay, so this is your expand opcode technique. I hope that in the future, if any question comes, any variation comes in the GATE exam, you will be able to handle. Also, you can solve that question within 30 seconds using the bit pattern method. Okay, using that method, you can solve the question within 30 seconds. Okay, this is what you can do. So thank you, everyone. Please give your feedback. Okay, please give your feedback. If you are watching this video on the GoClasses YouTube channel, then please share your feedback in the comments. And if you are watching this video on the GoClasses computer organization course on the website or on the application, then please share your feedback in the comments below. Okay, so please share your feedback. Okay, anyone has any doubt, let me know. Anyone has any doubt, please tell me. In the expand opcode technique, in the instruction format, whatever we have seen, all the concepts we have seen, all the questions we have seen, anyone has any doubt, let me know. Okay, there is no doubt. Okay, thank you, everyone. Please share your feedback in the comments. Please do that. Okay, thank you.